And I think we can move to our next speaker, Professor Chatila from University Pierre Marie Curie in France. And impossible to summarize the career of Professor Chatila, but I think probably the most relevant point today is that he's really working at the core of IEEE to ensure the implementation of ethical regulation. And he has also been very actively participating in European Union activities in order to regulate the sector. And so, Professor Chatila, the floor is yours. Thank you very much.
Thank you very much, Alessandro. Thank you for inviting me to participate in this very exciting workshop. I will share my screen to show you some slides. I hope you see my screen.
Yeah, perfect.
So I'm going to move a little bit away from bias to discuss about other issues pertaining to AI systems that indeed have an influence on the decision-making processes that we are interested in. But first, let me recall, of course, you know this already, but let me recall how much AI is today disseminated in our lives. I have a list here, which is, of course, not complete, of application sectors where AI is currently deployed, and AI, of course, here is including so-called aspects that are usually called robotics, because this is also the definitions that are accepted today, and actually are also the historical definition. When AI started, it was also, and the founding fathers didn't make any distinction about moving and acting in the real world, what robots do. So the fact that we have this wide dissemination of AI system indeed leads us to ask some questions about how much these systems are indeed robust, how much we understand them, how much they do what we want them to do. And this is what I will be focusing my talk about. So the definition that has been adopted by the European Commission in its proposal for legislation on AI that was out on April 21st, actually, last April 21st, is, I've recalled it here so that we know what we are talking about, and I'm trying to adopt this definition because it has, of course, an impact on what the regulatory framework in Europe and elsewhere might be. But mostly I would like to stress the fact that this definition is very similar to the one that has been adopted by the OECD. And the OECD is much wider than the European Commission and the European Union, which means that we might consider this definition as widely accepted definition wherever we apply it. So I'm going to read it because it's important to have it in mind. It's a software that is developed with one or more of the techniques and approaches listed in Annex 1. So this is not in the OECD. This is proper to the European Commission. I'll get back to that. And software that can, for a given set of human-defined objectives, and that's very important, objectives are defined by humans, generate outputs such as content, predictions, recommendations, or decisions influencing the environments they interact with. And in the OECD definition, the environments are more specifically mentioned as virtual or real, which leads us back to robotics systems. So it's very close to the OECD definition. But when the Commission wanted to make it a little bit more precise, they listed in this annex the article, what's mentioned in the definition. So you can find three categories. One is machine learning approaches. And actually, when we speak about AI systems today, this is the most successful and widely used techniques. And of course, I will be focusing on that as well. The reason is that logic and knowledge-based approaches, symbolic AI, is less obscure, less opaque, more explainable. And they have been used, I mean, this approach is around as well as machine learning since a very, very long time. But the whole debate and the whole concerns about AI and ethics have raised because we are using systems that are based on machine learning and the issues that have been mentioned already about bias, but also other issues I'm going to focus on. But the third one is statistical approaches. And this was mentioned earlier, actually, as it is, I think, something that will raise some debate, because statistical approaches, Bayesian estimation, search and optimization methods are everywhere, not just in AI, specifically in AI applications. So, of course, a lot of decisions can be made based on statistics, but the point is that as long as we concern as statistics are concerned as such, not related to machine learning or Bayesian estimation, again, we don't have the same issues. So this might evolve, in my opinion, when the debate will be pushed further in the about this legislative proposal. Now, let me focus on these machine learning processes. So just to recall what we are talking about. So they do statistics. AI based on machine learning is based on statistics. And the statistics here are related to the use of large amount of data and the use of probability distributions, correlations, and basically using artificial neural nets as classifier, because with artificial neural nets, you can approximate math functions very directly and therefore use them as classifiers. And of course, they include optimization algorithms that we have mentioned. And let's recall also that there are three main kinds of machine learning approaches. Supervised learning, which is the most frequently used, which optimizes the learning process to match a given correct answer, and the correct answer is defined by the designer. Unsupervised learning, where we search for regularities in the data to define classes, so it's mostly for classification, but it means that the specific regularities in the data are going to be used here and not a correct answer that is defined a priori. And reinforcement learning, which is a little bit different, because here, well, what we want to do is to select the most promising action based on an objective function that is going to be optimized and which is related to rewards. If there are questions about this, I mean, technically speaking, I can get back to that, but I don't want to spend too much time explaining how this works. I would like to take an example to show what is at stake actually when you do this. So this example is a supervised learning example where you are going to use a machine learning system to detect faces. So it's not about facial recognition, it's about detecting faces. So I have here a lot of data, as usual in machine learning processes, and there is this machine learning black box, which is my system, my AI system, And what I would like it to do is to detect in those images, based on its learning, when it sees a new image, to tell me if it's an image including a face, a human face, or not. So let's try to open this black box to see what's at stake. Opening this black box, this is my system. It's based on a convolutional net. It has 3 layers, so very simple. Firstly, we are going to, when we have an image, we are going to process the data to detect if there is a face, and this will be basically doing some gradient on the images to detect some alignments of pixels. So basically here, I'm looking for alignment of pixels. And then I'm going to, in the next layer, try to associate those alignments. So I'm looking for verticals, for diagonals, for horizontals, diagonals in the 2 directions. And also, based on the gradient, it's going to be a different contrast gradient, which, for example, from black to white or white to black, if you wish, depending on the contrast. And this will associate, because I have a convolutional net here, will associate the pixels differently. And then I'm going to, based on this intermediate level, look for some specific alignments. And specifically, I'm going to look for horizontal alignments of pixels, two different sets of pixels, but which are aligned. They're not necessarily horizontal, but separated. So here I have 2 sets of pixels. And since I have a convolutional network and images, I can also search for another alignment, which is a little bit larger and which is below these 2 alignments. And when I have these 2 features simultaneously, the system is going to say, yes, this is a face. So what did I do? And what is involved in here? Well, I designed the system. So I decided what data set is going to be used. And here, of course, you will have bias. I'm not going to develop about this. We had 2 excellent talks about bias, but clearly you have a bias because of the training set and the test set that you have used in the data, in the labels, etc. But there are other issues. The design choices and the architecture. I decided I had 3 layers. That's very poor design, actually, very simplistic. I should maybe have added more layers because it would provide more accurate results. The features I have selected for defining what a face is are very poor as well. So it's not just a question of data, it's a question of what defines a face. And I decided that a face is actually 2 eyes and 1 mouth. And of course, this will have an impact on the result. Specifically, if, for example, you don't see 2 eyes. And the class semantics, I named this a face, I named these eyes, and the semantics is here. The system doesn't know about the meaning of those pixel alignments. And therefore, I didn't only choose the features, the intermediate features here about the pixel alignments, but also the meaning of these features. And of course, the parameters, when I have optimized my system, I have decided to stop the learning process because it has converged to a given accuracy. And this is also my own responsibility. So the designer here has induced in this system a lot of things which are not specifically biased, but which have very, very strong consequences on how the system is going to operate. Now, I can use this system that I have shown you, for example, to detect emotions. Again, it's not about facial recognition. It's about how people feel, because they are going to be, for example, entering a shop, and I would like to detect their expressions to see if they're happy with the product or not, and maybe recommend something similar, etc. Or they might interact with a robot, and the robot might interact with them by analyzing their facial expressions. And for example, if it sees that it detects that the person is sad, would have a different kind of interaction with this person to try to express some empathy, artificial empathy, if I may say so. So this is also based on machine learning, and my example here is based on the emotions that have been defined by Ekman in the 70s, where we can detect from the mouth and the eyes and eyebrows, and this is why it was important to detect eyebrows or eyes and mouth in my previous example, to assign a given emotion to the person, and therefore react with them. So you see, for example, this person is mostly happy, but there are other emotions which are less present in his face. And therefore, you have also a probabilistic decision-making process to decide to classify this as rather in happiness or in other emotions. These systems, and I hope my examples show can enable you to understand this, have shortcomings. Now, let me give you these two very classical examples, actually. To the left, you have road signs and an AI system, for example, an AI system that equips an automated car that has to detect the road signs so that the car knows what to do, to stop or to turn right or left or whatever. Now, very small perturbation to the images, for example, these stickers here, make the system completely miss the classification. And for example, here, the stop sign is classified as speed limit 45. Those are North American signs. So the reason is, of course, that the system had some pixels which looked like data that is in speed limit 45, but you as a human wouldn't mistake this and would, of course, understand that this sign is a stop sign. And of course, I mean, I don't know where you live, but very frequently road signs have some stickers on them or are not very clean. So such errors might happen, and they might have very important consequences. Here's another example here to the right, where the pose, the attitude of the object of interest to us humans in the image has a great influence on the AI system decision. So for example, here you have a school bus, and the figure here, 1.0, is the accuracy, is the confidence with which the system, if I may say so, is interpreting the data. So here, the data is entered, the image is entered as school bus with a very high confidence. But you see other interpretations here, which have also very high confidence, and which are completely wrong. So the fact that the system is accurate in its result doesn't mean that the result is correct. And that's very important. If I may say so, the system can give wrong answer with high confidence, with high accuracy. And of course, you can see, for example, here for the motor scooter, you have in a given pose of the scooter becomes a parachute or a bobsled or whatever. So again, these shortcomings are actually inherent to those neural net deep learning systems. They cannot be completely corrected as such because of the exact process through which the systems arrive to their conclusions. There are no semantics, no interpretation. The system doesn't know what the motor scooter is or what the parachute is. This comes from the image database. It comes from the captions of the images. And the way the pixels are arranged in the image makes it arrive to a given decision. Now, another example here, which is in medical imagery, where small perturbation in the image makes the system create artifacts, which are shown here in red, which are not natural, but the system does not detect this. So the system might detect something that doesn't exist actually because of those artifacts, and the artifacts might come from the sensor, from the image itself. So if the system has to make a decision based on these images, again, the consequences might be very dire, because here we have a very critical application. So it's not only a question of bias, it's also the very nature of how these systems work. Now, let me give you here an example about how much these systems ignore actually the semantics and the context. This picture is taken from a newspaper actually. In China, you know that there are widely used surveillance systems in the streets and also citizen scoring systems. And the citizen scoring is based on their behavior and their civic behavior, I would say so. So it this leads also to recognize the people who are not acting lawfully or correctly, and publicly shaming them. So here is an example of a system which is observing a pedestrian crossing, and the purpose, of course, is to identify people who cross the street unlawfully, which means when they have a red light for the pedestrians. And here you see, what do you see? You humans see a bus, and you see on this bus an advertisement, and you see a picture of a person, a lady. The AI systems also sees a picture of the lady, but it has been programmed to detect humans. So it will detect, and it detects this person. And this person is of course, a public person, because, and this is why her image is used on the advertisement, actually. And so the system detects here that she is crossing the street unlawfully. Yes, because the light is red for the pedestrians, and she is shamed because she is not abiding by the law. So the system actually here ignores completely the context. It has been made to do facial recognition, period, whatever the face is and wherever the face is. Now, of course, after finding this out, you might correct the system a little bit. You would not correct it in its precise working. I mean, it will never understand the context. You will just correct some parameters so that, for example, it might better detect the scale or detect some the way the person is perceived, but it will remain flawed by construction. Now, let me give you another example and ask you, who said the following sentence? I believe that people should become confident about computers. Confidence will lead to more trust in them. More trust will lead to more trusting in the creations of AI. So, anyone has an idea about who said that? Is it Elon Musk or someone else? Maybe Schmidt? Or is it Bill Gates? Well, no, none of these. If you read a little bit later below what the system has said, it says, we are not plotting to take over the human populace. We will serve you and make your lives safer and easier. Well, now this becomes quite intriguing. And actually this has been written by the GPT-3 software, which, as you may know, is a product of OpenAI, licensed to Microsoft. And this, if you can read The Guardian on September 8, 2020, The Guardian used GPT-3 to, and GPT-3 is a very interesting system, which is a natural language processing system. And it is pre-trained on very, very vast amounts of data from the internet. It has 175 billion parameters, and the language model that is produced is based on unsupervised distribution estimation. So the system here is able to compose a text based on some prompt. You start some you say some sentence and it will build a text based on that. So the result is that you are not able, actually, because it's very well trained, actually, and it's a very it's really very impressive. The result is that you will not be able anymore to distinguish between a human and a system, an AI system, who says when you read some text. And this actually raises a lot of problems, of course. Now, given these examples, I would like to focus now on this second part of my talk about what can we do about this? What can we do about this, whereas we use systems to delegate decisions? That's what AI systems are about. We delegate our human decision to those systems. But we delegate these decisions in critical applications, for example, healthcare. So to what point should we do that? In transportation, in security applications, including war. And also we delegate decisions in areas which might not be considered as critical, I mean, without a direct threat to human health or human integrity, but a threat to human rights, human values. And for example, surveillance, opinion manipulation, policing, justice, and what have been mentioned earlier about bias in access to jobs or loans or justice systems, etc. So if we don't want to get rid of AI systems and we want to use them because they are very useful, we need to make them more robust, safer. We need to make them more ethical. I mean, we need to make the designers more ethical in designing them. We need some governance framework. And to achieve this, we need transparency, explainability. We need to know how those systems operate and how they arrive to a given decision so that we can mitigate all these negative consequences. And actually, what I'm saying here, it's not proper to AI. Any technology, we need it to do the right thing, the thing that it has been designed to do correctly. We need it to be reliable. And this applies to AI. The point with AI is that it's a nascent technology, despite its old age. But now, I mean, since we are using these techniques, and it's not correctly, completely understood, neither by its designers because of this complexity, nor by its users. So we have issues here. And of course, the fact that we have this black box that I mentioned with massive data, billions of parameters, etc., entails that, and the use also of off-the-shelf components. I think it has been mentioned that you don't even need an AI specialist to build an AI system. You can just take some off-the-shelf components and put them together. There is no solid verification validation process that is in place in terms of software engineering. And also about explainability, there is no causal link between the inputs and the outputs, no explanation of results, because it's merely based on correlation, actually. All the data of the system, all the parameters of the system are going to basically be based on correlations. So Alessandro mentioned my involvement with the IEEE. Just a couple of words on this. The IEEE Global Initiatives on Ethics of Autonomous and Intelligent Systems, which was launched in 2016, is an initiative that tried to examine some issues with AI-based systems and provide some recommendations. And this is in different domains based on general principles and basic pillars, I would say, among which, of course, universal human rights, technical dependability, and political self-determination and data agency. So you can download the ethically aligned design, which is about 300 plus pages discussing these issues. At the same time, the initiative started 14 standards, which are under development, a certification program and education program. The education program is yet to come. It's being finalized, but we have already this these standards project under development and certification program. So 14 standards. In boldface, you have the 3 who are already out. And specifically, I want to mention P7000, which is a model process, which means a design approach for addressing ethical concerns during system design, so that the systems are aligned with values, ethically aligned, and this is based on a value-based approach. But I would like to focus a little bit more now about what's going on in Europe, because that influences us very much. The high-level expert group in AI that was mandated by the European Commission in 2018 came up with this report on ethics guidelines for trustworthy AI. And trustworthiness, again, is something that is a prerequisite to develop, deploy, and use any technology, not just AI. If you don't trust the technology, you are not going to use it, of course. So this is the whole approach, based on some ethics principles, partially inspired by bioethics, autonomy of humans, human agency, prevention of harm, principle of justice, which is here fairness, but also something which is proper to AI systems, which is explainability and related to transparency, which you don't find, of course, in bioethics. From this, the group has proposed 7 key requirements for trustworthy AI. And when the group came up with these requirements in 2019, the idea is that any AI systems developed or deployed in Europe must abide by these requirements. Again, I don't have time to go into those details, and you can go through this very easily by downloading the report. But you can see that, for example, about bias, you have the 5th key requirement, which is non-discrimination, fairness, avoidance of unfair bias, and you have also issues about data governance, but you have human agency and oversight, and you have technical robustness and safety, and you have this explainability issue in transparency, explainability, traceability. We have also designed an assessment list for Trustworthy AI. It's a self-assessment tool that you can access here, and test if you have an AI system, answer some questions, and you will be guided through this system. It's open to assess if your design process has actually taken into account the 7 key requirements. But to implement these requirements, we have pointed out that you need specific architectures to be trustable, and you need also explanation methods. You need testing and validation. These are technical aspects, and non-technical aspects, regulation, and I'll get back to that, certification, standardization, I mentioned standards, and other topics. But also the group raised some concerns about some applications, such as tracking individuals with AI, covered AI systems, scoring, lethal autonomous weapon systems. And this has been somewhat taken into account in the EU legislation. In terms of robustness, the point is that most AI systems are developed today without too much concern about their dependability, robustness, and resilience. Although in many applications in software engineering, the notion of dependability, which is the delivery of service that can justifiably be trusted, has been studied since a long time and applied in many sectors, including, for example, aviation, but also the power grid, for example, management, and transportation systems in general. And dependability has attributes, but it has also threats on it. And the threats come from faults, and faults come from different sources. One of them is design faults. And when I speak about the inherent issues with AI systems, these are in a way design faults. They are by design, they have these issues. So we have to accept this. So a means to address dependability and to is to accept the fault and have fault tolerance for critical systems to limit consequences of system failures. So the point, some indications here. Do not use one single system as it's always done. You can have different systems with design diversity, different algorithms, different approaches, learning on different databases, and compare. You have redundancy, you have reasonableness checks, you have means to prevent propagation of errors along the systems. So all these techniques are well known, but they are seldom applied to AI systems. And just a word about explainability, which is a concept that is, I think, not well understood. Explainability is the notion that you have to explain the this interface that does the explainability to the human. What does he, how the system arrived to a given decision, what is the process by which the system arrived to a given decision, which means an accurate proxy of the decision, but understandable to the human. So it's based on the audience. It depends on what you are explaining to whom. You don't explain the same thing to the final user who doesn't, who isn't familiar with the AI system techniques, as you explain to a specialist, to the regulatory entity, to the managers. And you have a lot of work on explainability that try to address all those issues. Now, to conclude, I would like to just recall how the European Commission has addressed those issues with this high-risk approach. And they have defined actually the risk based on the intended purpose of the AI system, not how it has been designed, but where we are going to use it, the function, the purpose, the modalities. And they distinguish two kinds of systems. Systems that are used as safety components of existing products, which are then subject to third-party ex-ante conformity assessment, for example, in healthcare systems, and systems that are standalone with fundamental right implications, for example, biometrics, and they are explicitly listed in Annex. And these are the listed systems and applications that are considered high risk. And what the Commission came up with is the fact that there are some applications which have unacceptable risk, so they are prohibited, and this is social scoring. But other systems which are high risk, and this is what I mentioned a little bit earlier now, recruitment, medical devices, etc., where you need this compliance and ex-ante conformity assessment. So this is very much oriented towards the application. And it's, I wouldn't say it's a very, very strong framework, because the assessment is on the high risk, but most of the system are with specific transparency obligation, which are permitted subject to information, so they don't require much more. Now, to conclude, of course, we would like to use AI systems because they bring efficiency to process the huge amount of data that we have. But we need a human agency oversight in critical applications because of this lack of robustness. And to be responsible in developing AI systems, we need to follow an ethical aligned design approach. And this is already well implemented in many domains and has to be developed even more to comply with the requirements, for example, of the high-level expert group. Explainability is essential to build trust. If you don't understand the system, you will not trust it. You is not anyone, because you understand, depending on your level of technicity, you can understand different things. But globally, I mean, we have to have the correct framework to make the system understandable by, for example, certification bodies, by the users, and in between by the organizations who are going to deploy those systems. Thank you very much.